paper that appeared in Matter recently, and I just couldn't resist talking about it. So rather first reading it and then talking about it. So that's about the title of the talk. And yeah, so I guess all of us know about parameterized algorithms. In one view, we can think of parameterized complexity as being trying to figure out the effect of secondary measurements on the complexity of a problem. Primary measurement is the input size, secondary measurement is anything else other than the input size. So for an NP-hat problem, we typically don't expect polynomial time algorithms, and we expect only exponential time algorithms, or at least super polynomial time algorithms. And the non-polynomial part, in parameterized complexity, we would like to confine it to a parameter. So that's I guess all of us know it. It's just for completeness that I restating it. Okay. So a parameterized problem looks like given a graph G, a parameter K, and say you want to find a solution if the graph has a solution of size K. And let's say that the problem is NP-hat, and so you do expect only exponential time algorithms, so the exponential factor is restricted to only a function of K. That's about it, that was enough for our purposes. And the model of computation is the usual one, the single processor computation. But now, what if we have multiple processes? What does that mean? That is one area of, that's one motivation to study distributed algorithms. So in distributed algorithms, what we have is not one processor, but a network of processes. Let's say we have n processes that perform the computation collectively. It's not one processor performing a computation, it's a group of processors performing a computation. Right. And each processor, I'm going to use node, vertex, processor interchangeably. Okay? And network and graph interchangeably. And each node has an identifier. Let's say there are n nodes or n processors in the network, and each processor has a unique ID, and the ID is of log inputs. That much information the processor has, or node has. And what else it does? It has only the local information. That is, it knows about its neighbors, nothing else. So I know my name and my friends. I don't even know their names. Maybe realistically it's not true. Let's say I don't know their locations. Let's put it that way. But I know that I have friends there and there and so on. Okay? So, like I said, each node knows only about the edges incident of it. So let's say we have 6 nodes in this graph. Each node has an identifier, and the first node, the node 1, has its it knows about its identifier and knows that it has 2 neighbors, and it knows that if it wants to communicate with those 2 neighbors, it can. This much information is all each node has. Okay? So this is what is called as a local information. Like I said, I'm not from distributed algorithms, so at any point of time you think my talk is not very complete or so, please stop me and feel free to interrupt me for clarification. Okay. So now, like I said, the nodes have to perform a computation collectively, but then they need to communicate because no node knows about anything else other than itself and its neighbors. Nothing else it knows. So how do you perform computation in this scenario? But one way is by exchanging messages. So there are a lot of models of distributed algorithms, but I'm going to focus on only one model, so I'm not going to go and explain the other models. Okay? So in the model that we are going to talk about, nodes communicate by exchanging messages. Okay? And we assume that every node has a global clock, or in fact a clock or a watch that's synchronized with us. It's not very hard to imagine that. Though not really realistic, but it's also not hard to imagine. Okay? So the computation proceeds in discrete time steps, which we call as a round. Okay? I'll explain what happens in a round, and once I explain that, now the running time is defined by the number of rounds. That's your time complexity in this set. Okay? So let me just explain with this. So we have again a 6-node graph. In one round, the vertex 2 can send some message to 1. It's its neighbor, it can do it. And 1 can send to 5, it's fine. 2 to 4, and so on. So this is how the communication happens. Okay? So now what happens in one round? Let me define what one round is.
One small clarification, sir. This is only on the number of rounds and not on the actual amount of information or bits.
There's another notion of function. This is the time complexity or the round complexity, but the equivalent to space complexity in our classical simulation computation, we have message complexity. So that is also well studied around. But for this talk, I will not be using any message complexity terms. That's why I did this. But yeah, that's a good question. So his point was, what about the amount of communication that's being transferred? Yes, that's also a measure of complexity, and that's called message complexity. Alright. So what happens in one round? In one round, each vertex computes with the information it has at any point of time. And for that, it is allowed unlimited resources. That is using the information that only it has. Let's say I have my own laptop, I can do whatever I want. I have an infinite, you can assume that I have infinite resources, unlimited resources. So that's what is called as a local computation, and that's unlimited. But my only problem is I don't have the entire information. I have the resources, but I don't have the entire information. Because I only know about me and my friends. So I'm allowed to compute. Let's say I'm a processor, I'm allowed to compute. Then I can send and receive messages. So like I told you that we can send and receive messages to neighbors. So at the beginning of a round, I can think of sending a message, and at the end of the same round, I can think of receiving a message from my neighbors. Not just from one neighbor, but from many other neighbors. Okay, I hope the round is clear. So I can perform, if I am a processor, I can perform local computation using the resources I have, unlimited resources. Then I can send a message to my neighbors, to all my neighbors or one neighbor or a subset of neighbors, anything is okay. Let's say at the beginning of the round. At the end of the round, I will also receive messages from my neighbors. Okay? So this is one round. Now, if I place no constraint on the size of the message that I send in a round per neighbor, then that model is called local model. That is, I am allowed to send any length message to my neighbors. Okay? That's the local model. If I constrain that, no, I can only send login bits per round per neighbor, then the model is called congested. Okay? Why login bits? My identifier at least I want to send to my neighbor, right? Because the person does not know my identifier. Only knows that I am a friend, but my location and all does not know. So at least to send that I would require this. So if I place a constraint on that, then it's a congested model. So I hope this is clear. Okay? So like I said, it only login messages per neighbor per round is allowed. Okay, so there are fundamental problems in distributed computing, which in central computing is trivial, but not so in the distributed computing. The first problem, I would need all this for the result that I'm actually going to present. So that's why I'll just give an overview of the problem definition and the result. I'll not be going into the algorithms for these problems. First is the broadcast problem. That is,
in the context model, you're allowed to send log. The message size is log. The
correct.
number of messages is also log.
No, let's say I have 10 neighbors. To each of the 10 neighbors, in one time step, I'm allowed to send login messages. So totally I'm sending 10 login. If I have n neighbors, it is n login. But per neighbor, it's only login bits. Okay. So, broadcast. Now, given a network or a graph G and a vertex V, let's say I have some information and we all form a network. I want to communicate that information to all of you. That is called broadcast. Let me assume that the size of the message that I'm going to broadcast to all of you is login bits. Okay? So that's the problem of broadcast. Then BFS tree. We all are the network, again you only have local information. We want to collectively compute a BFS tree. What do I mean compute a BFS tree? At the end of the computation, each of us will know which of the edges incident on us are in the tree. Okay? And at a particular root vertex. Okay? Next, leader election. Among all of us, at the end of the computation, we want to arrive at a consensus that this person is the leader, a unique leader. All of us should know the unique leader among us. That's the leader election. And learning the network. So all of us only have local information, but we want to know the entire information, the whole information. That is called learning the network. Have all nodes, learn the entire graph. Okay? These are the fundamental problems. What are the complexities? The first three problems in congest model, that is where you have constraint on the message size. You can solve these problems in diameter terms, order diameter terms. Diameter is the diameter of the underlying network. Okay. For the learning network problem, in local model you can achieve diameter rounds, but in congest you require n rounds. You can think of that you need to, intuitively it's like you need to send the edge information. If you want to know the whole graph, you need to know its edges. And you're constrained in the congest model that you can't send too much of information in one round per neighbor. So in some sense, n messages have to be sent. The endpoints of each edge has to be known for everybody. Only then you know the entire graph. Intuitively, I'm not being formal and precise, but this is the idea. So in congest model, you require m rounds. Actually, these are all tight also. So congest, it's order m rounds. Local, it's diameter rounds. The other problems, it's all congest diameter rounds. Congest diameter rounds means local also diameter rounds, because local is more liberal. Okay? Now, coming to the problem of the focus of the talk. Distributed vertex count. Okay, what is a vertex cover problem? You given a graph G on n vertices. You want to find a minimum size set of vertices that hits every edge. So you take any edge, at least one endpoint should be in the vertex cover. Obviously, the whole vertex set is a vertex cover. That's not interesting. You want a minimum size set. That is a vertex cover. This is a minimum vertex cover problem. Okay. So the example that's given, the black vertices form a vertex cover. Okay. So a few clarifications. The communication graph as a network is same as the graph on which the vertex cover is decided. That's the first assumption. They're not very unrealistic. And at the end of the computation, what does each vertex know? Each vertex knows if it is in the solution or not. So let's say you have a flag. I know if I'm in the vertex cover or not. That's it. Okay? So this is what is the output of the algorithm. What is an easy algorithm? Have the leader. I said you can compute a leader in diameter rounds. You spend diameter time, compute a leader. That leader, you will ensure that you send all the whole graph to the leader, which again is learning the network. You can do it in order n rounds in the congest and diameter is order in the local model it's diameter rounds. And you have the leader learn the entire graph. Now the leader can perform unlimited local computation. She or she can compute a minimum vertex cover and inform that to all of us. That's all. It's a very easy algorithm. So what's the complexity? In local model it's order diameter rounds. In congest it is order n rounds.
It's applicable. But this leader, what is it serving? Can you take a real-time network? What does it mean? The leader election. So, how do you exactly elect the leader?
How do you elect the leader is the algorithm, but why do you need a leader is like, why would you need a leader?
My thing is, without knowing the network, you can't elect a leader. So if I'm voting, I need to know everyone. So there should be at least the cost of learning the network, right? Because each node should.
No, you need not know the entire information. Like it's possible that among the network, the one who has the alphabetically least is the leader. The first person who comes in the order is the leader. Why not? It's just a representative kind, right? It's not like an election where you elect a chief minister or a prime minister. It's just a representative.
The word elect itself.
Okay.
You have to designate somebody as leader. How do you do that? Representative.
Representative. Okay, actually, I probably said leader selection. Or choosing a representative, but it's usually called leader election in the literature.
But once you select that, you should tell each node that this is it.
Broadcast you can do, the leader knows, and you have to broadcast. Or in the process, you would already have come up with the leader. But yeah, that's specifically the algorithm that finds the leader. Alright, so this is an easy algorithm.
This one I can simply view as 3 steps, right? Like a leader selection, then local learning by the leader, and then a broadcast.
Different, yes. This is what it is. And overall time is this actually. So these are the low bounds that are already known in the literature. So you know that, okay, m is worst case n square. We assume that the input graph is connected. So n square congest rounds, that's a very easy algorithm, and there are low bounds that are also known. Okay? And there are no non-trivial exact algorithms from in the distributed setting known for vertex. Okay, there are a lot of approximation algorithms. 2 minus epsilon, or in other words, 1 plus epsilon, and so on, and a lot of upper bounds and lower bounds known. But in the problem of computing an exact, that is a minimum vertex cover, not much is known other than this trivial algorithm and a non-trivial lower bound. Okay. So, what is our setting now? What is the parameterized distributed vertex cover problem? It's the decision version of the problem. There is given a network G and integer k. You want to know if G has a vertex cover of size at most. Okay. That's the question. And the same assumptions. The computation graph is same as the graph on which the vertex cover is required. At the end of the computation, each vertex should know if it is. So here you need to have the notion of a k vertex cover, because there will be multiple k vertex covers. But you know, in some sense, every vertex should know if it is in that particular k vertex cover that we have found or not. This is one sense, the one reason why we need a leader. Leader will compute one vertex cover and send that information to everyone. Otherwise, I will compute 1k vertex cover, you will compute 1k vertex cover, because all of us can learn the networking at the same time. But then having the leader is useful here because that person can compute one particular k vertex cover if it is there, and then send it to us, so that we are the same page. Computing minimum vertex cover is also included. Most the distributed models assume this, because a lot of lower bounds are even for this model. And but there are some distributed models that don't have unlimited local computation also, but most popular ones do have this. Yeah. So the major complexity of the complexity is in the communication, learning the. Okay. So I hope what we require at the end of the algorithm is clear. Every vertex should know if it is in the vertex cover or not, or if there is no vertex cover, that information also every vertex should know at the end of the computation. Okay. And the parameter I said is k. So we hope to get an order f of k round complexity. We have n square complexity in the congest model and diameter complexity in the local model. We want that particular complexity to be bounded by some function of k, where k is our solution sets. That's the goal of that. This is this paper. Or rather one of the goals. So for that, a problem that's intermediate, it's an auxiliary problem that's used is parameterized diameter approximation. That is, the authors given order k rounds, or let's say k rounds algorithm that terminates with all, that is, there is an algorithm, deterministic algorithm, that terminates in k rounds. At the end of k rounds, all vertices will say small if the diameter of the graph is at most k. All vertices will say large if the diameter of the graph is greater than 2k. So that's why it's an approximation, it's not exact. And they could say small or large in the third case, in the last case, but there will be nuns. Either we all say small or we all say large. But if we say large, it means that the diameter is definitely at least k plus 1. If we say small, definitely the diameter is at most 2. Okay. This algorithm I will explain at the end. Okay. Using this algorithm, we will see what are the results we get. Okay. So let's assume that we have that particular algorithm. Now we are in the local model. So in the slide at the right top, I will mention whether it's congest or local in each.
It's like actually the regression which you use in the computing kernel for vertex. The regression that you use to compute the kernel for vertex.
Yes.
Can you use that regression then?
Definitely. How is that local? We are going to use that.
So like if the vertex knows it is going to be and it is larger than k plus 1, then it has to be in solution.
I agree. So what do you think the round complexity of that algorithm will be? Just think about actually that's the second algorithm that I'm going to discuss.
So at one point in time, all the vertices can know their degrees.
Yeah, their degrees they know, yes.
So in one round, they'll remove all those edges.
Graph could get disconnected, diameter would change. When you say remove all those vertices, diameter would change. And graph could get disconnected. But that's exactly what we're going to discuss with slight fixes. But yeah. First, we're going to check if the diameter is bounded by 2k in k rounds. So if vertices report large, we know that the diameter is greater than or equal to 2k plus 1. In that case, a k vertex cover cannot exist. You already have a path that requires at least k plus 1 vertices to be in the vertex cover. So you cannot have a vertex cover size k. All vertices can just say report until the flag is complete. If all vertices report small, then we know that the diameter is bounded by 4k. Now what can you do? You can learn the entire graph. We are the local model. So you can learn the entire graph in diameter terms. And diameter is only 4k, at most 4k. So in order k rounds, you will learn the entire graph. And at a leader in k rounds, leader can compute a minimum vertex cover in unit time step, because local computation is free, and broadcast it to other vertices in k rounds. So it either notifies that it's there, this is what I say. Either it says that there is no vertex cover to all the vertices, or if there is a k vertex cover, it sends that information to all the vertices. Very simple. So overall round complexity is k rounds. I hope that's clear. So it's not so hard. One of the reasons why this works very easily is that vertex cover and diameter are related. If the diameter is huge, vertex cover cannot be small. But it also works for other problems like matching, dominating set, edge dominating set, feedback vertex set, and feedback edge set. Also, in the local model, you can achieve the same round complexity, but a lot of fixes are required. Because if a k matching exists, matching is unusual matching, diameter need not be 1, not necessary. So it's not so easily to not follow from this algorithm, but with certain fixes for all these problems, we can achieve a round complexity of k rounds in the local model. Now let's come to the congest one. So this will be the remaining part of the talk. Okay? And this is where we use the parameterization. Okay. So why can't we adopt the algorithm that we mentioned in the previous slide for the congest model also? There's just one step. Everything will still go through. All the steps will go through at the same time complexity rounds. In congest model, it takes m rounds. In local model, it only took diameter rounds. So if the diameter was 4K, that step was also only 4K. But in the congest model, that step is m. This is the problem. So how do we improve this step? This is the focus of the congest. So now let's first focus on a guarantee version. That is, let us assume that the network has a vertex cover of size. We'll see how to remove this assumption. We will eventually remove it. Okay, suppose the graph has a k vertex cover. Okay, which means the diameter has to be 2k, at most 2k. Because if the diameter is again at least 2k plus 1, we cannot have a vertex cover of 6k, but you will assume it. Okay. Now, let's have this algorithm. Find the leader vertex in k rounds, which you can. Because in diameter rounds you can, and the diameter is 2. Now, here we apply our parameterization. Now, if the vertex is of degree greater than k, it has to be in any k vertex. So it can just set its flag to 1, meaning that I am in the vertex cover, and give this information to the neighbors and just keep it. Right? To send the information to its neighbors, one round is what is it. Okay. Now, if I have no friends, why will I be in any vertex cover, or rather, why will I be in a minimum vertex cover at least? So I don't have to be. So even if I don't have any friends, that is, if a vertex does not have any neighbors, it can still set this flag appropriately, in this case to 0. Again, there's nothing to inform actually, there's nothing to inform. It can just keep it. But we do assume the graph, input graph is connected, so this is probably unlikely to happen. But just for completeness, I'm saying. So now, any vertex is still active, has degree at most. And we are still in the guarantee version. We know that we have a vertex cover of size k at most. Okay. So any vertex that is not yet terminated has degree at most k. So the graph has k square active edges because there is a vertex cover of size k, and k vertices. If you have assumed that you have removed the think that you have removed the vertices of high degree, which have to be in any k vertex cover. So the remaining vertices have to cover. How many edges can each of the remaining vertices cover? At most k for each of them. And there can be only k of them, so k into k square. The graph cannot have more than k square edges. Now the graph size is less. The size of the graph that you want to learn is less. Still the input graph size is huge. But you don't need to learn the input graph. You only need to learn a subgraph, which is this subgraph. Okay? So that takes k square edges. Same usual algorithm. And the leader will compute a minimum vertex cover and again notify each vertex in this solution. Okay. So let's say that but the catch is that we have assumed that there is a k vertex cover, which of course it's not a reasonable assumption. So we need to remove the assumption. So let's assume that this algorithm has a round complexity of ck square, where c is a constant. So now let's consider a general network. It could have a k vertex cover, it need not have a k vertex cover, which is what we have to determine. Okay. So first let's just check if the diameter is bounded by 2k in again k rounds. If vertices report large, then good, we can't have a k vertex cover. If the vertices report small, diameter is bounded, you can compute a leader and a BFS pre-rooted at that leader in k rounds, which we can do. Then we run the algorithm, the guarantee algorithm now for ck rounds. That guarantee algorithm assumes that there is a k vertex cover, but we are running it on a graph that need not have a k vertex cover. So we run it for only ck rounds. So if it is guaranteed to not terminate within that, we can conclude that there is no k vertex cover. Because if it had a k vertex cover, it would have terminated in sequence. So this part is easy. Now, if it had terminated, it has computed some vertex cover, we need to check that it is indeed a k vertex cover. If you just think about it, you will see that it's not trivial to see that what it outputs is a k vertex cover. It is a vertex cover is fine, it need not be a k vertex cover because the algorithm assumes that there is a k vertex cover, which it need not be true. So, but nevertheless it is terminated, so it is computed a vertex cover. We need to check if it is indeed a k vertex cover, that is its size is k. That would take another k rounds. Alright, that's the reason why we need to have a BFS tree rooted at a leader. So what we'll essentially do is from the leaf, you compute the size of the subtree at each leaf and propagate that information to your parent. At any point of time, when I mean subtree, the vertices that are in the vertex cover of the subtree. At any point of time, you see that the vertex cover size has reached k, more than k, you just stop and broadcast saying that no, there is no k vertex cover. I'm going to make a bit fast, but I don't think it's hard to see. So the overall round complexity is k square in the congest. Alright, so now all that remains is how do we solve the diameter test? Because both the algorithms use the diameter test. How do we solve that particular problem? let me just reiterate the problem. What is the problem? We want a k round algorithm. In k rounds, what is the algorithm supposed to do? It should, all the vertices should say small if the diameter of the graph is very small, that is at most k. All vertices should say large if the diameter of the graph is greater than 2k. And in the other case, when the diameter is between k plus 1 and 2k, we can say small or large, but we have to be uniform. All of us should either say small or all of us should either say large. Okay? So if we say large, diameter is at least k plus 1. If we say small, diameter is at most 2. This is what we want. Okay. How do we do this? Phase 1, k rounds. It's very simple. In each round, every vertex sends the minimum ID that it has seen so far. Minimum ID I mean identifier. In the first round, I know only my ID. I will send that information to all my neighbors. I would have also received the IDs of my neighbors. So in the second round, I'll see the minimum ID among the IDs that I have seen and send the minimum to again all my neighbors. I will also receive, you get the algorithm? In the first k rounds I will repeat this. So at each point of time, I look at the minimum identifiers that I have and send that to my neighbors. I will also receive that this is a uniform algorithm, meaning every vertex does this operation. So I will also receive. Okay. So at the end of phase 1, each vertex V has the minimum ID xv. Let me call it xv. That's the thing so far. So this xv is actually the minimum identifier in a k hop neighborhood. If I look at my k distance neighbors, in k rounds, I would have got the minimum among this particular subgroup for every vertex. So the xv's could be different for every vertex, but this is what xv's interpretation is. Okay? Okay, so this is what happens. At the end of k rounds, every vertex has an ID called x of v. So 1 has x of 1, 6 has x of 6, and so on. Now, if the diameter is at most k, all xv's have to be the same, because that information in k rounds we would have seen. Okay? So if your diameter was at most k, then all xv's would be identical. Just a consideration. Now, so first k rounds is over. Now we are going to spend another 2k rounds, 2k plus 1 rounds. What are we going to do? In each round again, every vertex is going to send the minimum xu that it has seen and the maximum xu that it has seen. So at the end of the first phase, I have xv. Xv need not be my identifier. It is the minimum identifier in my k distance subgraph, k distance neighborhood. Okay. So what am I going to do in the first one? I am going to send yv is equal to xv, zv is equal to xv to my x. I will also receive. I did not say that. I said if the diameter is bounded by k, then the xv's are identical.
So now at this stage, in k rounds, we can broadcast whatever they have. And if some rows receive different values, then we don't have the diameter k.
Yeah? Yes, I agree. Correct.
Still in 2k rounds, we can have the same diameter.
1 minute. Okay, but no instance need not be true, right? If I can see a difference, then it's a no. No, see, in k rounds, I can only see my k distance neighborhood. But I could be far off from another vertex, right? That information I don't have yet.
If all the xv's are identical, then it's not necessary that.
Exactly. I agree that this is true. If diameter is at most k, xv's will be identical. But if xv's are identical, it doesn't mean that the diameter is at most k. And but first of all, how do we know that the xv's are identical?
Like 2K.
How? 2k?
Everybody talking each round.
Let's say I have an xv. There's a different xv very far off. That's not within 2k.
The IDs of somebody.
Yes.
So that means my ID, the common ID
Mm-hmm.
has reached everyone.
If the diameter is?
So if everybody has got the same minimum,
Okay.
that means the minimum ID has reached everybody in the case.
That's true. But how do we determine that?
That is fact. If it is, if it's at most, then the diameter is at most. Yeah.
Okay, so suppose we have the minimum ID in, if we have the same ID in, yeah, then it's
It's determining is that.
yeah, determining is different. Yes, correct. Nice, this was the next one. So, what do we do now? So in the next 2k plus 1 rounds, what we do is every vertex sends its minimum xv that it has seen and the maximum xv that it has seen. So I'm calling the minimum xv as yv and the maximum xv as zv. Okay. Initial round, both will be same as xv. The xv that is computed at the previous KLs. Okay. So now let's see what happens in this case. So at the end, every vertex has its current zv and yv. They could be same, they need not be same. Now, at the end of phase 2, that is at the end of this, is this computation here? Okay, what am I sending at every round in this phase? Okay, at the end of phase 2, each vertex will say small if its yv and zv are same, and say large if its yv is not same as zv. That's all. Okay, this is what it is. So we need to prove that it's correct. But this is the algorithm. Okay, correctness we need to prove this. So I hope the algorithm is correct. Okay. So this is the algorithm. It obviously takes only order k rows. It's 2k plus 1 plus k. Okay. So now, if the diameter is at most k, then the xv's are identical. So if you consider that the xv's are identical, whatever you do, or whatever yv's, zv's you send, it's all going to be the same. So even at the end of 2k plus 1 plus k rounds, you will still have the same xv. So what is this bill report? Yeah, this is what they were trying to say. Yeah, I didn't get that. Okay. Now, if the diameter is between k plus 1 and 2k, then, see the diameter is between k plus 1 and 2k. But you're running the algorithm for 2k plus 1 rounds, 2k plus 1 plus k rounds. So you would have got the information of yv and zv. Since you're running it for 2k plus 1 rounds, you would have got the global yv and global zv. And now, so all yv's, we have the same yv's, we have the same zv's. They need not be same among themselves. But my yv is same as your yv is same as that person's yv, and so on. Similarly, it's for zv's. So, all vertices either report small or report large. This is what we insist on. I hope this part is clear. They report small if the yv and zv are same, large if they are different. So now, suppose the diameter is at least 2k plus 1. Now let's consider the vertex V. This is the vertex V, and let's consider the vertex P, which is xv. P could be V also, it's possible. xv is the minimum identified in the k of label, the first k rounds that we ran the algorithm for. Okay? Okay. So, we have V, we have x of V is P. Now, since the diameter is at least 2k plus 1, there should be a vertex Q that is of distance equal to k plus 1 from P. If not, suppose all vertices have a distance at most k from P, then the diameter is at most 2k plus 1. But we said that the diameter is greater. Okay, I have missed out in strict inequality. Okay. Is that clear? So my point is, there is a vertex Q that is of distance equal to k plus 1 from P, where P is x of P. Okay. So now if you notice, the distance between V and Q is at most 2k plus 1. And we are running the second phase for 2k plus 1 rounds. Okay? So the yv and zv that Q has would have propagated to V. V will have that information. Alright? Because we are running it for 2k plus 1 rounds, and the distance between V and Q is at most 2k plus 1. The diameter of the graph could be huge, really huge. All that is guaranteed is at least 2k plus 1. But it could be very large. Though it is very large, V and Q are not that far apart. That's the point I'm making. Okay? So, at the end of k rounds, since P and Q are at a distance equal to k plus 1, their xv's couldn't have been same. Because they wouldn't have got that information in k rounds. Because phase 1 is run only for k rounds. So, at the end of phase 1, x of Q is not equal to P. And what does V have as x of P? X of V is P. It couldn't have seen x of Q. Now, after k plus 1 rounds, the information of x of Q would have gone to P. And after an additional k rounds of phase 2, it would have gone to V. Because V and Q are at a distance at most 2k plus 1. So, we would know that the difference, that is, if it has an xv, it has an xp now, we know that they are different. So, it has a yv, zv which are different. So, it will say match. And this is for an arbitrary vertex, so it's true for every vertex. Every vertex will tell match. This is what we wanted. So, this is the last slide of the talk. So, I was talking about upper bounds, and there are also lower bounds that are known for the problem in the parameterized setting. So these are the bounds that are known. So we saw for vertex cover in the congest model, k-square bounds algorithm we saw using kernelization, and it is almost empty. That's been shown. And the local model we saw k-round algorithm. That was very easy using the diameter approximation algorithm again, but that's also tidy. And similar results are also true for independent set. But the independent set is again, I think the independent set is harder than vertex cover in some sense, even in this session. So n-square algorithm is a trivial algorithm, learning the entire graph in n rounds, n is n square. And lower bound is also known. And the local algorithm that we discussed works for many problems, including independent set. So this is the summary of this now. But the interesting thing here is that one thing is how do we combine kernelization in the distributed setting? See, in our kernelization, many kernelization algorithms that we have seen so far, we also compute a global, say, maximum matching. We compute a maximum matching in many kernels. We compute a global structure of the graph that's very useful. We are on polynomial time, and that structure we compute in polynomial time. But in distributed setting, how do you do that? That is not very clear. So, or rather, is this the right way to bring parameterized complexity into distributed setting? Even that is not clear. So, like I said, I've just started taking distributed algorithms, and yeah. So, what are the notions of parameter, meaningful notions of parameter, and how do we incorporate parameterized complexity in distributed algorithms is yet to be explored. So, that's my one of my current interests. So, thanks a lot, and if there are any questions, I'll be happy to answer.